So our next speaker is Professor Stefan Williams from the University of Sydney. And he will talk about multi-robot sensing, perception, and deployment in marine environments.
Thanks to the organizers for inviting me to talk today, and thanks for coming along. I know it's been a long day of workshops, and very much looking forward to the conference ahead. So I took the title Multi-Robot Sensing and Perception in Extreme Environments and thought about that in the context of a lot of the work that I do in marine robotics in particular. And in looking around, I found this figure from the USGS describing underwater environments. And there's a number of these that we can think about, and we can think about many of them as extreme. So we can think about reefs as rugose underwater environments. You want to be close to the sea floor. You might want to be collecting visual imagery. So you have to be able to operate over very complex natural terrains. There are deep water environments where there's a lot of geophysical activity. There's a lot of interesting science to be had in these deep water environments. And further extreme environments happens once you get up into the coastal environment. So what I've done is organize the talk around these three sort of extreme environments from marine robotics, and I'll talk about some of the work that we've done in each of these areas over the years. And I will put in a fourth area that I think is not represented here, and which we're starting to think about, but haven't done a lot of work in. So for those of you who don't know me, I'm at the Australian Centre for Field Robotics. I run the Marine Robotics program there. We've been working in the marine robotics space for many years, thinking about development of platforms and sensing, navigation mapping, plane control, and a lot of work on data analytics. So how do we collect data and deliver that to support studies in ecology, archaeology, geoscience. We work with a lot of partners around the world, really look for motivating applications to use robotic platforms in the environment. And a big part of our funding over 15 years or so came from a program funded by the Australian federal government looking at investing in science infrastructure. This is about a $250,000 investment in infrastructure to support marine science, including the deployment of an array of moorings around the country, Argo floats. We've got a glider fleet. They equip ships and animals that are tagged. And we ran an AUV facility over that 15-year period. And I think this has been a really powerful investment on the part of the federal government in Australia to encourage collaboration in science and having designated marine science as a key thing for the country. And so we were able, through this program, to really develop a strong operational program deploying autonomous underwater vehicle systems around Australia, thinking about how we could track the impact of changing climate, changing oceanographic conditions on reefs around the country. This also allowed us to work in a variety of international collaborations. So we've done work supporting ecology, archaeology, geoscience deployments around the world. So thinking about how we can collect marine imagery or marine seafloor imagery and inform a variety of different studies with many different platforms. And so I'll touch on some of the outcomes of that work over the last 15 years or so. And I'll start with some of our work in reefs. And I'd contend that this is an extreme environment. So we're putting robots very close to the sea floor. Light attenuates very quickly underwater. We carry lights. We need to operate in close proximity to very complex structures. This is our vehicle, Sirius. This was in Greece over a first century BC shipwreck. But you can see the vehicle operating very close to the sea floor. You'll see the strobes illuminating the sea floor. We covered about 10,000 square meters of seafloor, built detailed three-dimensional maps of this wreck site, which was then used to further excavate this site. And so I think this is a characteristic of an extreme environment. We've seen some examples of drones flying around for us, but I think these operating AUVs close to the seafloor is a challenging thing to do. We think about doing this with many robots. We've done quite a few deployments where we've got ship time to bring platforms from partners around the world to study some of these seafloor environments. So here we've got AUVs, gliders, drifting floats. We had a little Gantt chart that we were using to kind of manually keep track of where our different assets were going in and out of the water, where the ships were to be positioned, doing a lot of the work kind of manually, and I'll show how we started thinking about automating some of that process. But we were still in a situation having many people operating a relatively few number of robots. But it's a great experience to be out in the open ocean working in this sort of area. And the sorts of thing we were thinking about is how do you combine remote sense data with in-situ observation to build detailed models of underwater environments. So it's a multi-sensing problem combining acoustic data with optical observations to build models and then to do some site selection. So figure out where should I put my robot next in order to collect the most informative subsequent samples. And we've set this up in practice using some learning frameworks where we're looking at automatically clustering imagery, looking for common image or common seafloor areas, using some unsupervised clustering techniques. We're using some bathymetric autoencoders to characterize the structure of the seafloor. And then we're learning a joint model between these two things. So learning where we can find particular habitats based on a combination of the acoustic multi-beam data collected either by a ship or by another robot, and then visual data, which gets clustered into these sort of groups, which we labeled after the fact. We can then label each image that we've taken with the robot, and we can then project out and build a model that predicts where I might find particular habitat types within this environment. I can also think about the uncertainty of that model. I can look at both the epistemic and aleatoric uncertainty. One models the uncertainty in the classification, the other models the uncertainty in the model itself. And what I want to do is drive down that model uncertainty as much as I can by selecting where to put my robot next. And I'll show some examples of this in a minute. What this looks like in practice is we get out into the middle of, in this case, this is some videos from a cruise we did in Hawaii. We have a map-based interface up on the ship. We're communicating with the captain who's moving a very large vessel around. We've got teams on small boats. We've got AUVs being deployed and recovered. We've got gliders going off and being deployed. And we're thinking about how do we coordinate all of these different platforms. What happened in practice was that we'd get up every morning, everybody would have a coffee at 7 in the morning, and we'd say, okay, what are we doing today? And there was gliders going in, there was a couple of different AUVs being deployed, there was multiple ships, the crane being needed to be getting things in and out. And so we started at 7 in the morning, and by 5:30 we wanted all gear out and back on the ship, and everybody ready for dinner. And inevitably, the glider would go off and we wouldn't hear it from it for a while, and we weren't sure exactly where it was. It was whale season in Hawaii, so there was whales all over the place. And occasionally the captain would say, well, we can't move for the next half an hour while whales get out of the way. And occasionally the AUVs didn't do exactly what they were meant to do. And then dinner's coming up, and we ended up in a situation of either aborting missions, moving vessels, thinking about leaving platforms floating on the surface, which is a risk. And the risk was always, there was a lot of negotiation going on to avoid the situation of everybody missing dinner. And so we put all this into a risk-aware planning tool. So a team from MIT were with us. They were starting to model these scenarios. So how do we actually put all these constraints into a big multi-objective optimization to say, okay, where and when should we be deploying and recovering vehicles? And towards the end of the cruise, they were starting to get this all humming along, and we had a great day. We had all the equipment going, and they came and they said, we're going to miss dinner. I said, no, we'll be all right. And inevitably, dinner was delayed, and we had to get our gear out late. So I think there's a lot of thinking about how do you plan these multi-vehicle deployments using tools like this to help inform scheduling and not having to rely on sort of intuition and hoping for the best. Another thing we've been thinking about is how we can rethink these benthic surveys to go from AUVs that cost hundreds or even millions of dollars and are expensive to deploy, maintain, and run. So if we take a lot of the sensors off, if we take a lot of the hardware off of these systems, can we do something simpler? So can we deploy imaging floats and take a leaf out of the oceanographer's playbook where they're deploying drifting floats to collect oceanographic data. So can we put cameras on drifting floats and do useful science with these? And one of the first things we did here was we took our robots and we drove them around and we put in some of these floats. And in fact, this is an unscheduled near collision because inevitably, whenever we had two vehicles operating in near proximity to the other, they would immediately head for one another. And so here we had to acoustically retask this drifting float because we could see that the AUV was on a collision course with it. So we started thinking about it, but we then started building these drifting floats. So we're building small, low-cost floats that have 1 degree of freedom. They go up and down, they control their depth, they have a little altimeter, relatively cheap altimeter, they float along in the current. We put them into Sydney Harbor and saw some not so nice parts of Sydney Harbor. We took them further up north, offshore of a place called Coffs Harbor. These are in some marine protected areas, nice coral reefs. So we said, okay, well, we can collect useful information with these platforms. We then got a WAM-V autonomous surface vessel. We built a mechanism to allow us to both see the deployment in that video and recovery. So it's a little arm that can reach down, grab the floats, stick them into a holster. We could deploy 4 of these platforms simultaneously. And we thought, okay, now we've got this multi-robot system consisting of a surface vessel designed to deploy and recover the floats. We were working with some colleagues at UTS who were building models of the oceanographic currents and predicting where the floats might go so that we could then optimize where we dropped off the floats and then where we recovered them at the end of a mission. So looking at sort of optimization of the deployment and recovery with this team of vehicles. So we had a bathymetric map of one of these points. This is in the south of Sydney. We had people, we had the WAM-V, we had some trials that showed that we could get these floats to sort of descend to an altitude of about 2 meters and drift along with the current. We take some images. We did our clustering sort of work. We then, so we had a prior deployment of an AUV in this area. So we run the AUV over this bit of reef. What we're interested in is really characterizing this bit of reef without having to deploy it. So that was our first deployment. We then thought about, okay, where should we put these vehicles? And these are successive deployments of the floats, which each of those deployments were selected based on optimizing the uncertainty of the resulting model. So we were putting the floats where we thought we could drive down the uncertainty in the model. And so what this looked like is, and here we've put some labels on the sand of kelp, reef in the kelp. And you can see we've marked the image locations with those 3 labels. We've done 1 deployment, so the first deployment of the floats, there's a lot of uncertainty up in this area. We're really not sure what's going on, particularly at the margins between what looks like flat and more complex reef areas. We then plan, observe, re-estimate, rebuild our model, look at the resulting uncertainty, so we really started to drive down the uncertainty in the habitat associations between the imagery and the underlying bathymetry, and then we do our third deployment. So we're doing this cycle of build a model, collect some data, refine the model, figure out where we should put the vehicles to go next. So I think that's a good example of sort of using multiple vehicles in the context of doing this sort of habitat mapping exercise. The next environment I wanted to think about was in deep water. So we've done a lot of work over the years building particular sensors. We don't operate vehicles ourselves at these sorts of depths, but we've built sensors. We've participated in quite a few cruises. One cruise a few years ago, we were actually here in Japan, just south of here, down near Okinawa. There's some artificial vent systems. So these are actually vents that have been drilled. So they've gone in and they've actually drilled into the core and induced hydrothermal vent activity. And we had two vehicles in this case. One was flying at 8 meters, so with a very sensitive camera and lighting systems, and then one was flying at 2 meters. And over sort of a similar amount of time, you can see the coverage that you're getting at those two different times. So there's a real trade-off between flying high and getting a big swath, flying low and having a much smaller area that you can cover. But the trade-off is the resolution. And so what we end up with is these are drill guides that are left on the seafloor. This is an old drill site, so it's actually drilled into this hydrothermally active seafloor. And the white bits here are bacterial mats that are essentially feeding off the hydrothermal activity. And you can see the resolution of these sorts of these cruises, and you can see actually, if you look here, these are all little lobsters that are sitting around this vent hole, sort of living off the bacterial mats and things that are living in those areas. And an interesting thing to look at is when the scientists then went and annotated the imagery, this is one of the areas that was surveyed at 8 meters. This was the 2-meter altitude surveys, which is a significantly higher resolution. You can see they could only see 2 species of organism at this resolution. But when we zoomed in and got a much higher resolution survey at this lower altitude, you get a much, many more instances of these bivalves and you know, things that are growing around there. So combining data from multiple different resolutions, I think, is an example where we're trying to provide more richer information for the scientists we're working with. This then informed some surveys that were done by a colleague at Southampton using a combination of AUVs and ROVs equipped with camera systems. They were doing very large-scale surveys. They used some of the work that we do on the unsupervised clustering to find areas of higher hydrothermal activity, which were characterized by these bacterial mats. And then they, again, were able to target particular areas of the seafloor. And you can see the mismatch in resolution between flying at 10 meters and flying at 2 meters. So these crowds are much easier to see what sort of the detail when you're down low. And this has implications for some of our learning techniques. So published a paper last year at ICRA looking at the unsupervised domain adaptation between data collected by different vehicles at different altitudes in different environments. So we were looking at being able to use some scaling, some bilinear cooling, and a couple other things to learn the relationship in an unsupervised way to allow us to adapt across different data sets. So we have to be conscious of the conditions under which we're collecting this data when we start deploying some of these machine learning tools. And if we're careful about this, we can find that the classification accuracy, so the tightness of those clusters becomes much tighter if we're accounting for the differences in the way this data was collected. Another example of a sort of deep water habitat survey that we did was in, this is in the Colombo caldera. This is Santorini in Greece. There's an active volcano here. The objective here was actually to find active hydrothermal vents. So we took the multi-beam map of the caldera, did unsupervised clustering of the bathymetric profiles. These dots here are previous area where there was some sampling, where there was known vent sites. The objective was to find new venting systems within this area. They were deploying ROVs with cameras, but also gliders doing sampling within the water column. So really coordinating between the water column sampling and looking for these vents. And in fact, by looking at the clusters of data in that little black box, they sort of blanked out everything except for one of the clusters, which was associated with prior vent activity. They were actually able to find new vent systems based on this unsupervised clustering of the bathymetric data. So able to identify where there was likely hydrothermal activity. Final example I wanted to touch on was in coastal environments. So as we're getting up into very shallow environments, significant challenges with deploying and safely collecting data in these sorts of environments, We've just wrapped up a Trusted Autonomous Systems funded project looking at autonomous littoral survey. So it's an academic industry partnership with about a dozen organizations involved. We're looking at novel AUV systems for nearshore operation, planning and control of multi-robot task allocation, anomaly detection, so finding unusual things in that environment. And there was one of the partners, Splendors, who was working on a crawler which could go and kind of investigate these anomalies. So our responsibility really was to deliver AUVs capable of operating in those nearshore environments, so very flexible, maneuverable platforms, so these vehicles can turn on the spot, they can dive, they can still operate for 6 to 8 hours at a go, but they're able to collect seafloor imagery in close proximity to the seafloor, even in these quite shallow environments. We developed tools to allow these platforms to operate in nearshore environments, building detailed visual models and 3D bathymetry from the stereo cameras that those vehicles carry. And here we're into a couple of meters of water depth. So quite nearshore operations. And we're particularly looking for unusual objects. In this case, we put a target into the environment to see if we could find it. We got some images of that. We then looked at anomaly detection techniques using a variational autoencoder to look at the reconstruction loss. So things that were unusual were not able to be reconstructed very well using the features that were learned from the background. And we're able to deploy these sorts of algorithms both on the AV imagery, but also on some of the imagery that was collected by the crawler. We found that if we accounted for the spatial proximity of some of these observations, we would get a tighter cluster of unusual objects. The other thing we were trialing was an automatic planning technique. So here, an operator would designate a couple of areas for the AUVs to survey. They would prioritize these, and in this case, this southern site was seen as a priority. We simulated the loss of one of the vehicles, and then the automatic planner then automatically reroutes the top vehicle. It takes a little while for it to realize that the first vehicle's disappeared. It'll then head down and start surveying in the bottom box. So combining multi-vehicle planning with the near-shore sensing capabilities. I said I'd add one more extreme environment to this figure, which I don't think is represented in this particular representation. And I'd say that's polar regions. So if we want to get under ice and really understand what's happening in our polar regions, I think there's some really interesting challenges to operating in those environments. I think there's lots of opportunities to use robotic systems in those polar environments to help us understand contributions to climate change, to changing ice fields. I think there has to be a bit of a paradigm shift from low numbers of very high cost assets to more disposable platforms such as gliders. Given the risks here, the prospect of losing a multi-million-dollar vehicle parking under the ice is pretty horrific, I think, to anybody who's tried raising funding for doing research. So if we can get to the point of these tens to low hundreds of thousands of dollars per vehicle, I think that'll transform the way that we do this kind of science. I think there's also some interesting other approaches that people are using to collect this kind of data. These are very low cost robotic platforms, so instrumenting seals. There's a lot of work going on putting these sensor payloads under ice with the help of these somewhat unwilling participants, but a lot of interesting science being done with that sort of platform. And I'd like to sort of finish up on some thoughts about the relative, the design space, and this is some work of Rich Camillia at Woods Hole, the design space of platforms that are being used as autonomous underwater vehicles and autonomous gliders in that polar space. So along this axis, and this sort of similar to something like Milford showed earlier, massive vehicle on this axis and range in kilometers along this axis. Typically, as the mass comes down, the endurance is also limited. But gliders are starting to really fill a niche where you're having small, relatively low-cost vehicles with long ranges. I would argue we could, make an analogy between mass and dollars. both in terms of the cost of the vehicles, but also in terms of the cost of deploying those platforms. So large ships cost a lot of money to operate. And I'd probably add one extra little sensing payload platform up here. These guys are relatively low cost and have incredible ranges. So I think there's some interesting things we can do and learn from the science community about the way that we collect data. So in conclusion, I think we've demonstrated several examples of multi-robot sensing and perception in extreme environments, both from all the way from the coastal zone down into deep water. There's some really exciting challenges and novel applications. Marine robotics have really transformed our understanding of our oceans in a lot of ways, and I think lots of future challenges in long-range teaming, machine learning tools for interpreting the data that we're collecting, increasing the operational tempo of autonomous marine systems, so getting from the 50 people to run 5 robots to maybe 5 people running 50 robots at some point. And I think there's a lot of exciting things happening in the intervention space. So once we start trying to interact with the environment, doing sample return, management of offshore infrastructure, I think there's some really exciting challenges there. And we are always looking for great students and postdocs to come and join us down in Sydney. Take some questions.
Thank you, Professor Williams. So we have 5 minutes for questions.
Hey, thank you. Very exciting work. I saw that you for the classification of the benthic habitat, you would use bathymetric data and also images.
Yeah.
Do you happen to also use backscatter data from the multi-beam?
We don't. No. We could. We have not typically been using backscatter information. We're just using the essentially measures of ergosity with an unsupervised autoencoder to identify features of interest, and that's how we've been doing it. We haven't used backscatter.
Is it something that you're looking into, or is it not interesting? Or
I think it is interesting. I think there is a lot of information that could come out of the backscatter, particularly the difference between hard bottom, sand and mud and things like that. So yes, definitely. We haven't reliably been having access to bathymetric data. When people give us bathymetry, often it's just the bathymetry, and we don't have the backscatter data available. So absolutely, it's a possibility, and we can certainly put it into the framework without too much difficulty, but not something we've been focused on.
all right, thank you.
I have a question. In terms of all these regions of exploration and coverage, so by using the multi-robot systems, does it improve the resolution, or is it only to increase the area of coverage?
In a lot of cases, you get complementary sensors on the platform. So for example, that example of the work that was done in the Colombo caldera, you had ROVs with cameras and a variety of sensors on board, and then gliders collecting water column data. So you're getting complementary data with which to understand the whole environment. In a lot of these cases, we're not actually communicating those in real time, so the decision making isn't happening necessarily in a closed loop, but it certainly could.
Thank you.
So for the floaters that you mentioned, it looked like they had stereo camera on the bottom, or what?
No, it's just a monocular camera.
Just monocular.
Yes, yeah.
So how are you?
One of them had an arm sticking out. That was a light sticking out.
So how are you doing localization for that? Do they use GPS on the surface?
We have a GPS when it comes to the surface, but then there was also an acoustic tag on those, so we could track them with USBL while they were underway.
Okay.
Which gives us, good enough for what we're doing with those particular ones.
Thanks.
So one more question from me. I'm just curious, like how do you get the scale of the environment if you don't use like a stereo or anything, just with a monocular camera? Like you also build like a representation.
Yeah, so for the AUVs, we always carry stereo, so we get scale from that. For the floats, we have done some work on using a combination of the depth measurements. So you can pop the floats up and down, measure the change in depth, and that'll correlate with the change in the scale of the imagery. So you can resolve scale if you're kind of moving up and down the verticals.
Okay. Yeah.
Thanks.
Thank you, Professor Williams.